Welcome to the final session of the 2021 BA Winchester webinar. As mentioned previously, all the lectures are being held on Zoom and live streamed to YouTube, and the recordings will be available to watch on our YouTube channel shortly after the event. You can ask questions by typing them into the Q&A on Zoom or the comments in YouTube, and we'll answer them at the end of the presentation. It's my pleasure to hand over to Alan Lorraine, the President of the BAA.
Thank you very much indeed, Andy, and welcome to everybody for the final session of the BAA Winchester 2021 session, the Alfred Curtis Memorial Lecture. The lecture is held each year to recognise the contribution made by Alfred Curtis, who started the event, if you were listening to Alan Dowdle earlier on this afternoon, some 55 years ago. The Winchester weekend has long been one of my favourite BAA events, held each year, provided the opportunity of meeting up with people. There were sort of numerous meals over the weekend, and it gave people the opportunity to sit down with a group of different people, perhaps at every meal, and to widen your sort of people that you knew within the BAA. And the following year, you would bump into the same sort of people again. So that was a really enjoyable side of it. I was initially held at King Alfred's College, actually in Winchester, and more recently has moved out to the nearby Sparshot College, which had the advantage that had a dark sky environment, and on some occasions we were able to use telescopes. And looking out the window this evening with the clouds very thick and rain, that wouldn't have been one of those occasions this year anyway. Sadly, we aren't able to meet in person this year, but we hope that you've enjoyed our programme today, which is focused on exoplanets. We're hoping, as far as meetings face-to-face are concerned, to perhaps be able to hold our AGM in October at the Institute of Physics. But a note for your diary, the Winchester Weekend 2022 will be held on the weekend of the 8th, 9th and 10th of April. So that's one for your diary. Initially, I'd like to express my thanks to Anne Davis. Anne Davis has worked tirelessly for Winchester over many years and has been responsible again this year for putting the speakers together. And without her, there wouldn't really be a sort of Winchester weekend of the same quality. I'd also like to express my thanks to Andy Wilson. That Andy acts as the administration sort of person behind the scene, providing the technical advice, but also actually sort of when asking the questions on behalf of the people, the questions and answer session at the end, adding in some very useful comments and helping people out as well. I'd also like to thank Alan Dowdle for his introductions this afternoon, also to Roger Dimmick, the Exoplanet section director, for their sort of work this afternoon, which has made it a really interesting day. Earlier this afternoon, David Brown from Warwick University gave us an excellent talk about the ESA CHEOPS mission, and we're going to be continuing that theme this evening. I'm pleased to confirm that the Alfred Curtis Memorial Lecture this year will be given by Dr. Jessie Christiansen. Jessie is an astrophysicist with NASA's Exoplanet Institute at Caltech, where she searches for, characterises and catalogues planets orbiting other stars. In 2018, she was awarded the NASA Exceptional Engineering Achievement Medal for her role with the successful NASA Kepler mission, which discovered thousands of exoplanets and revealed that rocky planets are common throughout the galaxy. She now works with the NASA TESS mission, the Transiting Exoplanet Survey satellite, to find and study the nearest planetary systems to Earth, systems that will be perfect for further study with the next generation of ground and space-based telescopes. It's my pleasure to welcome from California, Dr. Jessie Christiansen on an exoplanet far, far away. Over to you, Jessie.
Thank you so much. Thank you, Alan, and thank you, Anne, and everybody for setting up this weekend. And thank you so much for the invitation to give the Alfred Curtis Memorial Lecture. I read about Alfred, and, you know, as an astrophysicist and as an astronomer and someone who really loves interacting with the public, Alfred had the kind of service that I would aspire to be so dedicated and to give so much of himself to the BAA and to the Winchester Weekend and to the Royal Astronomical Society and all of his incredible gifts and service and achievements. So this is a real honor for me. So thank you very much for inviting me to come today. And I'm so excited that you guys are having a day devoted to exoplanets, which is clearly something that I live and think and breathe all the time. So today in this talk on an exoplanet far, far away, I wanted to take us on a journey through the development of the idea of exoplanets in real life and the development of the idea of exoplanets in fiction and where those overlap and where they diverge, because I think it's really interesting what we got right and what we got wrong. So let's get into it. And we're going to have the same first slide issue we always have. Okay, so if this was a more interactive talk, if I was there in person, I would ask a show of hands who recognizes this. This might help. This is the Enterprise, and this planet is Vulcan. This is a rocky planet that's Spock's homeworld from Star Trek. This is where Spock comes from, Vulcan, the planet Vulcan. Classic sci-fi world, goes back 50 years, classic rocky planet. It's also known as, because astronomers are very, very bad at naming things. As any of you amateur astronomers out there who've gone and looked at something in the sky, it's probably had like 8 names. Astronomers shouldn't be in charge of naming things. It's also known as Vulcanus A2, Navasa 2, or 40 Eridani A2. And I'm going to apologize right now at the start of this talk for the names that astronomers give things, because they're garbage. They're really, really rubbish. Okay, so this is Vulcan. So Vulcan has been, in the zeitgeist, in the cultural sci-fi moment for a while, but it's actually not the first planet that was in the cultural zeitgeist. So let's talk a little bit about the history of our thinking about exoplanets. More than 2,000 years ago, 600 BC, the Greek philosophers were talking about the infinity and the singularity of Earth. So Earth as a construct is the thing that they were standing on. These were Greek philosophers that would talk about anything. And they were like, this Earth, is it singular or is it plural? Like, are there many Earths or are there just one? And they were talking about this in a purely abstract thought experiment kind of way. But what they were really arguing about was whether there could be other worlds out there that were like Earth, that were Earth-like planets. So I would argue these are some of the very first conversations that we have as the human race about the idea of other worlds, other planets. Plato and Aristotle actually argued that the Earth was unique, that there wouldn't ever be anything else that was truly Earth-like. In fiction, the first time we really start to see fictional narratives explore the idea of stories set on other worlds is Dante's Paradise around the year 1300. And he's, building this paradise where Earth is at the center and there's all these spheres around it. This is well before our Copernican model of the solar system. And he's building these stories where the other worlds in our solar system are places where stories can happen. So this is a real interesting evolution in our thinking about like, where can stories be set? Okay. So now we jump forward to the Renaissance. Exciting time to be a scientist, not an exciting time to have bad things to say about the Roman Church. Giordano Bruno was both. He was an Italian mathematician and philosopher who had this quote, which I'll read. There are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system. And I'll leave it as an exercise to the listener as to which 7 he's talking about in 1592. Okay, so he's like, look, the sky is full of stars. Our star has a bunch of planets. Why wouldn't they have planets? It just makes sense. He was actually burned at the stake in part for saying this. He also, as I mentioned, said a bunch of silly stuff about the Catholic Church at a time when it was bad to do that. But one of the reasons he was burned at the stake was claiming the plurality of worlds, for claiming that there were other planets out there. Interestingly enough, 100 years later, Isaac Newton, who was, a quite religious man himself, didn't have any problem reconciling these two ideas that there could be a God and that there could be other planets. He was like, that's fine. He's just God of all of them. No issues here. So yes, Giordano Bruno, 1592. He's like, there's planets everywhere. So the idea has evolved now. Planets everywhere. Okay, skipping forward through the 1700s and 1800s, we really start to see large bodies of works and large themes appearing in the literature of where stories are set. So like the 1700s, the moon is this mystic place in the sky that people are starting to look at through telescopes and see features. So they're writing stories set on the moon. Skip to the 1800s, and now we have like canals on Mars, and people are starting to be able to resolve those features. So we have this whole, set of literature set on stories on Mars. So we're really starting to explore these worlds as places for ideas to foster. And, one of the exciting things about science fiction is that, the stories are still very much, anthropological stories. Like they're stories about us and how we find ourselves and how we live and how we relate to other people, but we just get to set them in cool places and ask the questions a different way. And this is like part of the evolution we see through science fiction and science. Okay, getting back to the science side. So 400 years after Giordano Bruno's like, there's planets everywhere, and we still hadn't found any. And it turns out planets are really hard to find. Stars are really big and bright, and planets are very small and dim. So the canonical explanation is it's like looking for a firefly in front of a floodlight. Like it's just so hard to see the contrast difference between those two. So Otto Struve, an astronomer in 1952, says, okay, what if we could look at a star and measure its velocity? So there's ways we can measure stellar velocity. Basically, the stellar spectrum either gets blue shifted or red shifted as the star is coming towards us or away from us. And astronomers had already seen this in binary stars, two stars going around each other, and you would see the relative velocities of the stars changing. One would be coming towards you and the other one would be going away. And so Otto Struve was like, okay, what if we took out one of those stars and put a planet in instead? The velocity difference would be much smaller, but it could still be measurable. And this could be a way that we could find exoplanets. Now, at the time, this idea kind of fell completely flat, lead balloon. And, people were like, yeah, but how would you form a giant planet right next to a star? The giant planets in our solar system are multiple astronomical units away. They're very, very far away, much further away than Earth. How would you ever do this? This doesn't make sense. Like, we're not going to find that kind of planet because that kind of planet doesn't exist. So between 1952 and 1995, this paper was cited like 7 times. Everyone just ignored it. Okay. But in the 1950s and 1960s, we start to see, we have a technological revolution in our cultural moment. Things move to the screen. So we have like some of the first examples of other worlds and fictional worlds appearing on film, for instance, in the 1951 film, When Worlds Collide. And we have the first, for people who joined a bit early, we were talking about Doctor Who. We have some of the very first fictional planets appearing on television in the TV show, the British TV show, Doctor Who. So, what we see is this technological advance in the way we ingest our science fiction. At the same time, there's a technological advance in our ability to find planets. And in 1995, finally, telescopes get stable enough, spectrographs get precise enough that we finally find our first planet. After thousands of years of thinking about whether or not there are other planets, we finally find our first planet orbiting another star. And it's using the method that Struve proposed 40 years earlier to find the kind of planet that Struve predicted 40 years earlier. We found these giant planets orbiting incredibly close to their stars. We call them hot Jupiters, because we're bad at naming things, as I said. But this whole new class of planet that was discovered was the very first kind of planet that was discovered. And so now this paper, which had 7 citations in the first 40 years, has now had over 100 citations in the last 20 years, because everyone's like, wait, he totally called it. So that's science. That's kind of the way the field develops. And so interestingly, there's this parallelism. You can see the way I've kind of set this up in our advance in technology, in both our cultural lives and in our technological lives. So that's the end of that history lesson. So now we're up to now, and we have actually found over 4,000 planets now using a variety of techniques, but a lot of them found with this method that Otto Struve suggested. Now, we are finding thousands of planets. And as Alan said at the start, my role, I'm an archivist. I'm a NASA archivist at the NASA Exoplanet Archive. My role is, my day job, my project support, the role that I play for NASA is that I'm the one who takes all of the planets that get discovered and puts them in the Exoplanet Archive, me and a team of scientists and data analysts. So here's an example from 3 years ago, 2018. So I'm putting in this new planet. It's called HD 26965b. I'm sorry. They all have terrible names. But as you can see, I've had to put in all of these aliases because astronomers have 20 different names for the same bright star. It's appeared in so many different catalogs. It's got all these names. So as I'm putting it in 3 years ago, one of the aliases jumps out at me. And I'm like, 40 Eridani. 40 Eridani. Why do I know 40 Eridani? And so very, very short Google later, and I realized This is Vulcan's homeworld. This is Spock's planet. 40 Eridani A is the star system that Vulcan in Star Trek is located in. So here is a real image of the 40 Eridani system. It's a triple star system. So we have a bright star and a fainter binary. C and A is the bright star and C and B are the faint stars. And so in Star Trek, Vulcan is orbiting this star, 40 Eridani A. And in the real world, we found a planet orbiting 40 Eridani A, which is super cool. I was so excited when I found this out. It's not a rocky planet like the Vulcan in the Star Trek. It's one of these gas giants that we found close to the star. It's just, they're very easy to find relative to the other kinds of planets. And you can ask me about that if you want to know why. So it's kind of like we found Vulcan, but not yet, because it's a different kind of planet. But one of the things that we have found, one of the discoveries we've made since looking and finding these exoplanet systems, is that systems have lots of planets in them. Typically, you don't just find a star with one planet around it. Typically, you find a star with multiple planets around it, which kind of jives with our understanding of our solar system with 8 planets. But other stars, when we look at them, if we can look at them in enough detail, typically we find they have more than one planet. They have many planets. They have multi-planet systems. So even though the fact we haven't found a rocky planet around 40 Eridani A yet, there could be one there. So we could be close to finding the actual, equivalent to Vulcan, to Spock's homeworld. This is the one that I found that is closest to Vulcan. This is an artist's rendition. Every image of a planet that you're going to see in this talk is an artist's rendition. We're not at the point yet where we can resolve pictures of exoplanets around other stars. But this is Kepler 62F, which is a rocky planet around a star kind of like 40 Eridani A. So this is the closest we've found to Vulcan so far, Kepler 62F. So this discovery inspired me to see what else we could, find that was real life and also in science fiction. So I went through the Star Trek Memory Alpha Wiki, which is basically an online compilation of all of the Trekkers around the world have put all of the knowledge about Star Trek in this wiki. And there are 938 planets that have been visited in Star Trek that I could find in this. 51 of those had stars that I could map to a real star name in our encyclopedias of stars. Some of them I had to do a little bit of fudging, like Taura Alphus. I was like, okay, that's like Alpha Taurus. Like I can work out what star that is. So there were 51 stars that had real names. Of those, 7 actually have been found in the real world to have planets around them, including, for instance, 40 Eridani A. But one more system I wanted to talk about before I move on from Star Trek is Tau Ceti. So in the real world, Tau Ceti has been found to have 4 planets around it. This is another artist rendition of this Tau Ceti system. So here's I put this in specifically for the amateur astronomers. Here's the constellation Cetus. So Tau Ceti is this one here. So next time you're out and you can, it's the right time of year, go and look at the constellation Cetus. Tau Ceti is this one down at the bottom of this trapezoidal thing. It might be barely naked eye, but probably more like binoculars, because I think it's 6th magnitude. It depends how dark your sight is. But anyway, you can look with your eye and see a planet a star that has planets around it. This star's got 4 planets around it. So hopefully at some point, if you get a challenge from Peter and Paul, they'll be like, go and find all of the stars that you can find planets around. Anyway, so in the real world, it's got 4 planets around it. In the Star Trek universe, it also has 4 planets around it. So not only did they get the star right, they got the number of planets right. It's a 4-planet system in the Star Trek universe, which is so wild. One of the reasons in real life we're excited about Tau Ceti is because 2 of the planets, these 2 here, are very close to what we call the habitable zone. So the habitable zone basically describes the region. Here's a model of our solar system, where green is the habitable zone. It describes the region where if you took a planet basically exactly like Earth, like a rocky planet with an atmosphere, and you put it in the habitable zone, you could have liquid water on the surface. It's basically what the habitable zone means. We could have a whole different talk about why we define the habitable zone that way, but basically the short version is everything on Earth needs liquid water. So this is kind of the region from the star where if you had the right kind of atmosphere on the right kind of rock, you could have liquid water. And now if we look at Tau Ceti, this is kind of scaled to the same scale. So this is 1 AU, where Earth is 1 astronomical unit, the distance from Earth to the sun. So Tau Ceti has 1 planet just inside that and 1 planet just outside that, kind of like Venus and Mars in our solar system. So this one's probably too hot and this one's probably too cold, but that's still cool that it's got a bunch of planets right near the habitable zone. And that's one of the big discoveries out of the last 10 years of exoplanet hunting, is that planets are common, they're everywhere, and planets in the habitable zone seem to be common. And that's really exciting. We couldn't say that 10 years ago. We think habitable planets, rocky habitable planets, are common throughout the galaxy, which is wild. Anyway, so if there is life on these planets, on Tau, Ceti, E, and F, it's probably not exactly the same as our life. And we can have a whole separate discussion about why we're looking for our life. There's surely different kinds of life, and a lot of people are trying to come up with theoretical models for different chemical gradient pathways that could, end up with a self-replicating chain of proteins or something. But as so far, all we know is our kind of carbon-based, phosphorus-based life. Okay. This is Altair 4, another exciting planet. I just want to keep moving. Here is where you would find the equivalent of that planet. This is Cassiopeia. Okay, here's where I wanted to end up. The planets of the Whoniverse. So as we've talked about a bit, I'm a Doctor Who fan. So here's a pie chart of everywhere that Doctor Who has gone in their box in the last 58 years. If you had a box that could go anywhere in time and space, where would you spend most of your time? Did you say Earth? Because that's where Doctor Who spends most of their time, on Earth. It's a good for the budget, good for visiting historical periods, good for appealing to our anthropocentric points of view. But to be fair, Doctor Who spends most of their time at Earth. The next largest wedge of type of planet that Doctor Who visits is Earth-like. That's where they basically just put like a filter over the lens, and they're like, "Ooh, it's like Earth, but it's orange." Nice. Again, good for budget reasons. The interesting part here is that looking at the numbers of planets we found and the types of planets we found, 3/4 of the planets that we have found are not Earth-like. They're very un-Earth-like. So this is just an interesting, juxtaposition of like our expectation from science fiction, like what will all the planets in the galaxy look like, versus what we're finding, which is that the most common kind of planet seems to be larger than the Earth. We call it a super Earth, something between like 2 to 4 times the size of the Earth. Big. Why? We don't know. We're still working that out. The next biggest wedge of this pie is Earth-ish. This is where you're like in caves under a surface where the surface is like not habitable, and there's like, some gases and stuff, or, it's still basically, a rocky planet, but, in some way they've made it so that it's different enough. Very rarely Doctor Who goes somewhere properly uninhabitable. Like if anybody recognizes, this planet system down here, which I'll come back to in a minute, Midnight, sometimes they go to places that are truly uninhabitable, but very rarely, which is the exact opposite of what we find in real life, which is that almost every planet we have found so far will kill you horribly, quickly. We have found incredibly few planets that are actually habitable. So this is actually the inverse of real life. Space, sometimes Doctor Who is just in space and, visiting spaceships and stuff, like the whale in space or the dinosaurs on a spaceship episode. Sometimes they really genuinely go somewhere different, like a black hole or an asteroid belt or something that's disintegrating. Sometimes they do actually go to places that aren't just a rocky planet, but it's incredibly rare. And just the interesting part here is how different that is from reality. The pie of reality is the opposite of this. And I just want to shout out to JJ Eldridge, who actually scraped this information for me to turn into a pie chart. So thank you, JJ. Okay. So coming back to Midnight, this is a David Tennant episode. It's kind of like a bottle episode. There's a group of people trapped in a shuttle on this crystal planet. And the point is this crystal planet has this ionizing radiation essentially from the star, which is like sterilized the surface of the planet. But the surface is covered in crystals. Now, this is a graphic here that I'm showing of 55 Cancri E, which is a rocky world that we found orbiting incredibly close to its star. And the period's measured in hours. And so what happens to a rock if you heat it up and really put intense pressure on it? If it's a very, very carbon-rich rock, it turns into a diamond. So one of the theories for 55 Cancri E is that actually has a diamond layer inside. And, the headlines were all like, "Tiffany's, eat your heart out, largest diamond in the universe." That this planet actually has this like heated and crushed layer of carbon that has turned into some kind of crystalline structure like diamond. So this is the closest we've found to a crystal planet like Midnight. And I would say we actually got pretty close because it's not habitable and maybe very crystalline, but we're still working that out. It's really hard to look inside other planets. It's hard enough to detect them, let alone characterize them. So that's our next challenge for the next 20 years is now that we've found all these thousands of planets, what can we learn about them? Another system famous from Doctor Who is Gallifrey, and I wanted to point this one out in particular to just chat quickly about moons. So moons are also very, very common in our solar system. Almost all of the planets have moons. Almost all of them have multiple moons. Earth, in fact, being a proper planet-moon binary as compared to like Pluto-Charon, which is kind of like a planet-planet binary or dwarf-planet binary, is rare in our solar system. Most of our planets have multiple natural satellites. So this is something, given how common planets seem to be, and given how common multi-planet planet systems seem to be, we actually have a pretty high expectation that there are moons out there, given how ubiquitous they are in the solar system. But remember how hard it was when I said to find planets because they're so small compared to the size of the star. Now you have to go down another order of magnitude again in size and brightness to get to moons. So we're not there yet. There are some candidates from the Kepler data. I'll talk about Kepler in just a minute. But so far, we have not found any exomoons. We're hunting for them, but haven't found any yet. So we haven't found anything really truly Gallifrey-like yet. But we have found multi-planet systems like Gallifrey around multiple stars, which I'll come back to. Okay, so I've mentioned it a few times. This is Kepler. Kepler was a 1-meter telescope that NASA launched into space in 2009. It observed its original field of view, which is in the constellation Cygnus, for 4 years before some hardware failures meant it was unable to keep pointing in that direction. And in that 4 years, the goal was to find out how common planets like the Earth were. So for Kepler, planets like the Earth meant rocky planets in the habitable zone, which we've already discussed, in stars around stars like the sun. So roughly sun-like stars, boring middle-aged yellow stars. So Kepler ran for 4 years. And one of the things we found is that it seems like Earth-like planets in the habitable zones of sun-like stars are very common. Let me just play this again one more time so it can run while I'm going. We think something like 10 to 50% of stars like the sun have a rocky planet in the habitable zone. That's incredible because our galaxy, has something like 100 billion stars and something like 25% of those are stars like the sun. So that's 25 billion stars. So if something like 10 to 50% of those have rocky planets in the habitable zone, that's like 10 billion rocky planets in the habitable zones of sun-like stars in our galaxy, just our galaxy. And there's hundreds of billions of galaxies. That's so exciting for me to be able to say since I started working on the Kepler mission in 2010 and we had no idea. Now, I'm going to point something out slightly uncomfortable about this, which is that Kepler did not actually find any Earth-like planets in the habitable zones of sun-like stars, which might be disappointing to hear after I've just made this big claim about how common they are. What we found is what I'll show you on this next slide. So this is a schematic. This is the Earth and the sun. So in this schematic, the stars are all to scale with each other in terms of size and color. And the planets are all to scale with each other in terms of size and color, but the planets and the stars are not to scale. So in real life, Earth is 100th the size of the sun. So this is what we're looking for. We're looking for Earth around the sun. One of the very first things we found at Kepler 20e was a rocky planet incredibly close to its star. And so that was proof of concept that we could check one of those 3 boxes. We found rocky planets. This is so hot that the surface of this planet is just liquid magma. It's a lava world. It's getting roasted. It's thousands of degrees because it's so close to a star, but it's a rocky planet. One of the next things we found was Kepler 22b, which was the right distance from its star. So this is checking the second of those 3 boxes. And it was a sun-like-ish star. This is a K star instead of a G star, but pretty close. But it was too big. So this is more than twice the size of Earth. And that's about where we start thinking that they're not predominantly rocky planets with thin atmospheres anymore. They've accreted a lot of volatile material like Uranus and Neptune, and they're like big ice giants. So this is the right distance and the right kind of star, but the planet is too big. All right, so we kept hunting. One of the next things we found was Kepler 186f. This is a rocky planet in the habitable zone of a star that's not really like the sun. So this star here, you can see, is quite small and quite red. So it's an M dwarf. And I'm sure most of you have, like, you know, seen the different colored stars in the sky. M dwarfs are the most common kind of star in the galaxy. You know, like 70% of the stars in the galaxy are M dwarfs. But M dwarfs are different from our sun in the sense of the different kinds of radiation they put out. And for our purposes here, the problem is that M dwarfs put out a lot of their energy as high energy radiation, like UV and X-rays, the sorts of things that are bad for us on Earth. Like, you know, you're in England, and if you go outside and it's 30 degrees and sunny, you've got to put on your SPF or you're all going to fry to a crisp. I know, I've been there. So UV is bad. And X-rays, you know, that's the reason why your dentist makes you wear a lead apron when you go to the dentist and get an X-ray, because X-rays are bad. So it could be that planets like this that seem to be very common, we're excited by the fact that these planets seem to be common. It could be that they're all just totally sterilized by this high energy radiation, which would be kind of a bummer, because it seems like M dwarfs, which is the most common kind of planet, make a lot of rocky planets in the habitable zone. So if those planets were in fact habitable by something, that would greatly extend our habitable real estate in the galaxy if these kinds of planets were habitable. The thing is, we just don't know yet. So we're working on this really actively right now, whether rocky planets around M dwarfs could be habitable. The last exciting thing I wanted to tell you is this is Kepler 452b. So this is the right distance from the star, the right kind of star, and almost the right size. So this is about 1.5 to 1.6 times the radius of the Earth. So it's kind of right on the edge of where we expect things to stop being rocky. Doing a bunch of modeling about planet formation and how planet interiors are built and then atmospheres are accreted on top of them, 1.5 to 1.6 is kind of like on the hairy edge. So it's probably got about a 50-50 chance of being rocky. It's also, besides that, the signal in the data is very tentative. It's not a really strong detection in our data. So it could also just not be there. It could be a false positive. If it's there, it's got a 50-50 chance of being rocky. So this is the best we did. In terms of trying to find a rocky planet in the habitable zone of a star like the sun, this was the best we did. So how can I make a statement like 10 to 50% of stars like the sun have rocky planets in the habitable zone? Because we extrapolated, which is always dangerous, because that means you're assuming something about how the population of planets changes as a function of the distance from the star and the size. But we found heaps of things that are a bit closer into the star, and we found heaps of things that are a bit bigger. So if you extrapolate in both directions and say, what could the population here be, a bit smaller and a bit further out, we don't have a physical reason to believe that they would suddenly turn over and become less common again. So we think that they're actually very common just by extrapolating. But I wanted to say that because it is always a dangerous assumption just to extrapolate into a new area of space that you don't have good data. But in terms of these planets, what are our fictional counterparts? So lava worlds, we're going to switch franchises for a minute and jump to Star Wars. Mustafar, where Anakin Skywalker and Obi-Wan had their big fight, that was a lava world. So we have found equivalents to Mustafar. We have found lava worlds. This big Kepler 22, the planet that was too big, but it's the right temperature for liquid water. When we measure the density, it's actually pretty close to the average density being liquid water. So this could be an example of something we don't have in our solar system, which is a water world, like a pure, some kind of core in the middle, but a very deep water ocean on top of that. Which of course brings to mind Kevin Costner's classic Waterworld movie. And in fact, the very first one of these that we found, GJ1214b, was nicknamed Kevin by the astronomers who found it after Kevin Costner, because it seems to be some kind of water world. Okay, Kepler 186f, this was the rocky planet around the M star. We have rocky planets around M stars in fiction. Krypton, and then this whole thing that I was saying about the radiation around M stars, the reason Superman has his powers when he comes to Earth and our yellow star is because the radiation from the yellow star is so different from the radiation from the M star. I love that they incorporated this actual physics into the explanation of this like superhero origin story. So we have found rocky planets in the habitable zones of M stars like Krypton. And then the final, Kepler 452, assuming it exists, starting on the assumption that it exists, it's still not, because it's big, it's still not quite right. So I'm going to say that something like a truly Earth-like twin, like in science fiction, this would be like Beta Z from Star Trek or Caprica from Battlestar Galactica. We haven't found a true Earth twin yet, like something that we know is rocky, something that we know would be habitable, something that we know is around a star like the sun. So we're still not there yet. This kind of canonical world that everyone's been imagining for thousands of years, we still haven't found it. The hunt is on. And we will find it. We will find some, but we haven't yet. But we have found all sorts of amazing things that really, really excite the imagination, even if we haven't found, you know, the thing that would probably speak closest to our hearts. We haven't found, but we found a lot of things that speak to our heads. So this is another classic science fiction shot. This is from the 70s. This is, you know, nearly 50 years old now. And this is Luke Skywalker on his homeworld, Tatooine, looking off in the distance at a binary sunset. Now, this was before we'd even found planets. I just want to make sure you guys understand that. We hadn't detected no planets around other stars yet. Now we have found planets around binary stars like this. This is a graphic of Kepler 16b, which is one of the first planets that we found in these kind of circumbinary systems. We call them circumbinary because there's two stars in the middle close to each other going around each other. And then there's planets going around that binary star system, so circumbinary. And I really love this because George Lucas, again, in the absence of any actual information, even got the colors right. He's got a yellow star and a red star. He didn't get the sizes right. And, you know, this is an M dwarf, so it's smaller, but, you know, it's artistic license. He even got the colors right. It's wild. So that's Tatooine. This is a type of planet that we found. It's a gas giant near the center of our galaxy. So one of the techniques that we use to find planets is called microlensing. And it relies on the fact that anything with mass bends space-time. And I'm going to stop there because everything after that is either magic or relativity, which I don't want to get into too much depth. But basically, you can detect planets going in front of background stars because they lens the light, they magnify the light. So this is as far away a planet as we found. It's 26,000 light years away. It's almost in the center of our galaxy. And skipping franchises, perhaps one more time to the Marvel universe. Vormir, which is the Soul Stone planet, is described as like a desolate planet at the edge of existence. And this is as far away a planet as we've found so far, this Vormir, this desolate microlensing planet towards the center of the galaxy. So yay, we've got Marvel Universe planets in here too. Okay, one planet that people often bring up is Dune, as Arrakis from the Dune series. And it is a planet orbiting Canopus. Now, you guys know Canopus. It's one of the brightest stars in the sky. We haven't found any planets orbiting Canopus yet, but Canopus is a red giant. It's hard to find planets around red giants because remember the part about planets are small, stars are big, red giants are even bigger, hence the name giant. And so we have found planets around red giants, though. It's tricky, but it's possible. So we haven't found the equivalent of Dune yet, but we have found planets around all kinds of different stars. M stars, K stars, G stars, F stars, A stars, evolved stars, white dwarf stars. So those are stars that have gone all the way, have sloughed off their outer layers to become a planetary nebula, and now they're just a little cooling ball of carbon in the middle. In fact, kind of a cool story. It turns out that we had observations of exoplanets 100 years ago, and we didn't realize it. Carnegie Observatories, which is actually here in Pasadena, have these photographic plates of spectra of white dwarfs. And some of them show much more heavy elements, many more heavy elements than should be on the surface of a white dwarf, that they should just sink down straight away. And so now we understand, now that we've found planets so many places, and including around white dwarfs, now we understand that that's evidence that that white dwarf just recently swallowed a planet. Like the planet spiraled in and tore apart and got, accreted onto this white dwarf. And that's why we see this pollution on the surface of the white dwarf. Because of these planets getting torn apart and eaten. And this evidence, now that we look back, this evidence was there 100 years ago that we were observing planetary systems around white dwarfs and we just didn't know it. So I think that's really cool. And just again, speaking back to the fact that we have found planets in so many different places, far beyond what, we've expected from science fiction. Science fiction, it turns out, a lot of Earth-like planets, a lot of sun-like stars. And it's like, everywhere we look in the galaxy. We see free-floating planets, we see planets around dead stars, we see planets around brand new baby stars. We see planets everywhere. And so far, almost all of them will kill you, which is, you know, less exciting than they're everywhere, but still kind of amazing. One of the types of systems that we haven't found, I'm coming a little bit to the end now, so gird your loins for one more type of system. One of the types of systems that we're finding are common that weren't really very well represented in science fiction, if at all. Excuse me, my allergies are very bad today. One type of system that we found are very, very compact, dynamically packed systems. And so let me describe what that means. This is a graphic of TRAPPIST-1, which is a little tiny baby M dwarf. It's about as small a star can be and still be a star. If it was any smaller, it wouldn't have enough pressure in the center to start hydrogen and helium burning. So it would just be a brown dwarf. It would be a failed star. It's very small. It's only 8% the mass of our sun. And it has 7 rocky planets around it, all within the orbit of Mercury in our solar system. So the closest planet in our solar system, Mercury, with a period of like 87, 88 days, this is 7 planets inside that. And the only way that you can get so many planets packed in so close is because their periods are all related to each other. They're all in resonance. So we see resonances in our solar system. So the Galilean moons of Jupiter are in a 4:2:1 resonance if you measure their periods. Pluto and Neptune are in a 3:2 resonance. For every 3 times Neptune goes around, Pluto goes around twice. And the thing is, these resonances kind of lock the planets into place and they keep them stable because basically they're always trading the same amount of energy as they go past each other. So they keep the system stable. So what we're finding is lots of these systems with heaps of planets packed in really tightly. And we say dynamically packed, meaning you could not put one more planet in here without destabilizing the whole thing. And one of the reasons that's really interesting is because it tells us something about how these systems form. Before we found exoplanets, we only had our solar system to model. So when people, you know, for the last 100, 200 years were coming up with theories of like, how do planets form? How did our solar system form? If your theory didn't create a system with like inner rocky planets and some gas giants and some ice giants and maybe some belts all nicely spread out, then you were wrong. And you had to go back to the drawing board because, you know, we only knew of one kind of system and it looked like this. So. And we'd been taught by this point to think of ourselves as not special, right? Like there's no reason why our solar system should be special in any way. But what we found when we went out is that there are so many different kinds of planetary systems out there, including these very dynamically packed ones. Now, there are competing theories for how planets form and how they migrate to where we see them today. And some of them don't work with this kind of system. Some of them rely on planets interacting with each other, like Jupiter and Saturn switch places. Maybe they kick a 5th giant planet out of the solar system. You know, all these kinds of really big, violent interactions don't create this kind of ordered, stacked, you know, very careful system. This kind of system you can create if the material is all forming in a disk, and we think there's like a protoplanetary disk of dust and gas that's forming when the star forms. If they form in the disk while the disk is still there and then just start migrating slowly, then they, through the disk, you know, introduces a source of torque, of a pull on the planets. It's like they're trying to travel through molasses. And so they'll drift through the disk and then they'll get locked into a resonance with another planet. And then those 2 planets will drift and lock a 3rd planet in, and then they'll drift and lock a 4th planet in. So this can only happen like really smoothly and slowly and carefully over some period of time. Like if some giant planet comes barreling through here, these are all going to get scattered. And so that's some of the first evidence we have for which kinds of mechanisms work and how long they take and all that kind of stuff. This is my baby. Exoplanet scientists, you know, have their little like family portraits in their wallets of the planets that they found. So this is K2138, which is a system of now 6 planets orbiting a star. And it's also in one of these very tightly packed, compact configurations. Each of the 5 inner planets is in a 3:2 resonance with the next planet. So it's a whole chain of 3:2 resonances. Now, the reason why this is cool is because the 3:2 resonance, music relies on resonances like chords and intervals. These are all resonances between different frequencies. The 3:2 resonance is the perfect 5th interval, which people who, you know, study Western music theory, that's in the tonic chord. That's the 1 to 5 interval in the tonic chord. It's the first two notes of Twinkle, Twinkle, Little Star, for instance. So this system is playing music, and these people at System Sounds, which is a website that sonifies astronomical data so that people with different abilities can, access it. They turned it into a song. And so what I'm going to do, I'm going to play this video. Every time the planet goes in front of the star, it's going to play a note, and the frequency of the note is related to its period. So you'll hear all of these 3-2 resonances, and it sounds beautiful because it's a resonance. It's all happening like periodically. So let me get this started. And Alan, you tell me if you can't hear it. This is just your moment in Zen at the end of a very long, enthusiastic talk. Just listen to the 3-2 resonances of this planetary system. So that's K2138. It's a musical system. And one of the reasons I love it, not just because I got to publish it, but because it was found by citizen scientists. It was found by people at home helping us look through the data from Kepler to find these planets. There's just thousands and thousands and thousands, literally hundreds of thousands of data sets from Kepler that we've looked at with programs. But that the human eye hasn't necessarily gone and like examined for each one in detail. So this was actually found by people at home on their computers looking at the data to help us find dips. And so in my very last slide, I'm going to switch to TESS. So as we said at the start, so TESS, the Transiting Exoplanet Survey Satellite, is NASA's successor to the Kepler mission. Kepler ran out of fuel in 2018, so wasn't able to keep hunting for planets. But in 2018, we launched TESS. So there are some big differences between TESS and Kepler that you might be interested in. So as I said, Kepler was this big 1-meter telescope, a single 1-meter telescope that we launched into space. Here's TESS. So there are 4 cameras. These are 10-centimeter cameras. These are like off-the-shelf 10-centimeter cameras. I bet half of the people on this call have a bigger telescope than 10 centimeters. But the thing is, if you send a 10-centimeter telescope to space, you're above the atmosphere, you're above the clouds, you're above the sunshine, and you can actually do a lot. So where Kepler was a narrow, deep survey, looked at one patch of sky with this 1-meter telescope quite deeply, TESS is doing an all-sky survey with these much smaller cameras. So it's obviously focused on much brighter stars, but the sky coverage is incredible. It's going to do the whole sky. So where Kepler had this very specific statistical goal, we want to find out how common Earth-like planets are. TESS has a very different goal, which is we want to find all the nearby planets orbiting the brightest stars so that we can study those planets in more detail. Remember how I said we're just moving from detection to characterization? TESS is going to allow us to find the planets that we study for the next 100 years and examine their atmospheres and look for biosignatures and look for technosignatures and like really, really study in detail. So TESS has been operating for 3 years now, and a lot of the TESS data are going to that website that I had on the previous slide, planethunters.org. So if you're interested, especially like, during the pandemic, maybe people can't get out as much as they used to. If you're interested in helping us hunt for planets, all of the TESS data, which are very similar to the Kepler data and have yielded thousands of planet candidates so far, are on planethunters.org. And I would invite anyone who's interested to go and have a play with those data. It takes 2 minutes to learn how to spot a planet in the data. And then you can just go. And, for me, the exciting thing is I get to include citizen scientists and amateur astronomers on my papers, on my published papers. So the paper that we published on K2138 has 4 citizen scientists and a bunch of amateur astronomers on it because they were able to be so instrumental in the discovery and the characterization of the system. So to sum up, it's been thousands of years, but we finally got to the point where our technology has caught up with our imaginations and we're able to find these amazing worlds. And what we're finding is like even more interesting than all of the things that we imagined. A lot of the things we imagined did come true. We were able to find planets in some of these crazy places. But the types of planets and the distributions of the planets that we're finding are so different from what we expected or predicted that, truth is stranger than fiction, always true. So thank you very much again for having me today, and I'll be happy to take any questions now. Thank you. Should I, I think, Alan, you said you were going to moderate the questions.
Yeah, I'll do the moderating of questions. So thank you, Jessie, for a fascinating and very engaging talk. Seeing Altair 4 come up made me think back to Forbidden Planets, which I think must have been 60s, maybe 50s.
Yeah, I think it was actually 53. Wow. I can talk more about Forbidden Planet, but I was like, I gotta get through this.
Yes. And for just to remind everyone, you can do the Q&A at the bottom of the screen on Zoom, and on YouTube I'll also keep an eye out for any comments on there. I'm pleased to say we've got about 110 to 120 people with us across Zoom and YouTube this evening, or for this morning for you. So we have a question which has come in from Stephen Beath. I understand that planets have been observed around a neutron star. Are these planets that have survived the supernova event, or have they been captured post-supernova by the neutron star?
That's a really good question. So yes, we have some of the very, very first planets that were found, actually in 1992, before the 1995 ones that I talked about, were found around pulsars. So these are neutron stars that are spinning very, very, very fast, such that we can see the pulses coming towards us as they spin around. The jury is actually still out on whether these are first generation planets, so planets that existed around the original star and then survived. So there's been a lot of modeling of, what happens when it goes into a red giant phase. You always hear here, like, in 5 billion years, the sun will grow to swallow up the Earth. Well, actually, as the sun is growing, because the distribution of mass in the solar system is changing, the planets will actually start drifting outwards in their orbit. So there's a lot of modeling, like, would Earth drift out and survive, or Jupiter and Saturn drift out, and then the supernova happens. So we don't know yet whether they have survived this original explosion, or perhaps that the original explosion might destroy everything and then they've reformed, like there's been a second generation of planetary formation in that solar system from the material that's left behind. A lot of the planets that we find around these pulsars are small rocky planets, which would probably be the only thing you could make. Like, if you have an explosion that blows most of the dust and gas out of the system and creates these like beautiful planetary nebula and stuff that you see, there might not be much left to form planets. Or it could be that they've been captured. We've talked about that idea. So this is the idea that other planets nearby, like rogue planets, get captured by the star. Just statistically, that's a low likelihood of happening. We think that there are a lot of rogue planets in the galaxy, but we're still trying to work out how many. And you'd need a fairly large number to have a reasonable chance of catching one. So we're not sure if the math works out there yet. It seems like it's unlikely, but it's not impossible.
And so that was just on Tim Paul's question on the rogues. And now we have Chris Hooker, who's asking, I remember reading that moons of exoplanets can be detected by variations in the transit times of the planets. Can you comment on that?
Yes. So if you have a two-body system, a star and a planet, then Kepler's laws exactly describe the orbit of the planet around the star. And that will be exactly periodic, like every 2.5 days, the planet will exactly come back to this spot, and you'll be able to see it. If there are additional bodies in the system, like for instance, our solar system, we have the sun and 8 planets, then everything's pulling on everything else all the time. Jupiter's pulling on Earth, and Mars is pulling on Earth, and Earth is pulling on Mars. And so what actually happens is, instead of all of like 365.25 days for the Earth, instead of everything happening exactly on a period, the planets get tugged a little bit, and they're either a little bit early or a little bit late. In our solar system, it's a pretty small effect. It's minutes. If you were an alien civilization monitoring Earth, there would be some minutes. Sometimes it'll be a few minutes early, sometimes it'll be a few minutes late. It's not very long. But if you had a precise enough instrument that could measure the exact time that the planet was back at that exact spot, you'd be able to see this. Now, we have actually used this to discover planets, like additional planets in systems, by looking at the size of the deviation. So for instance, you see some planets that arrive hours early and hours late, and you can tell that must be because of something big that's probably close to a resonance, like the resonances we were talking about, because that would have the biggest effect in terms of swapping energy back and forth. So we do see planets that have deviations of hours from their expected period. So we expect that moons would do the same thing, but in terms of the size of the signal, it'll be really small. So, you know, Jupiter induces an effect on Earth, but the moon, our moon, induces a very small effect. So again, it's just a theoretically possible, but just in terms of our technology and the precision with which we can do transit timing, we're not quite there yet, but we're aiming to be there. It's a goal.
Thank you. And actually, I'll just go back to what I was saying before, because I think as I was reading the question, I confused myself, which was, there was a follow-up question from Tim Paul about, is there any way to detect rogue planets? And I think you answered that in your earlier.
Oh, so how we detect them. So there's two ways so far that we've detected them. One is microlensing, which I talked about earlier, which is just, you know, you monitor a background screen of stars, which typically for us is the center of the Milky Way, because that provides the densest background screen. And you wait for brightening events in those background stars. And that's because something is going in between you and the background star and magnifying it is using this lensing. So rogue planets do that. And that's one of the ways we found rogue planets is with microlensing. The other way that we've found rogue planets is with direct imaging. So just doing imaging surveys of the sky, like deep, typically infrared imaging surveys, because even though they're planets, they're still putting out some heat, you know, radiogenic heat and heat from contraction as the planet is forming and evolving. So they actually glow in the infrared just a little bit. So there's been a number of like all sky infrared surveys that have gone deeper and deeper, where you start to find these very cool, very small rogue planets. Typically, they're more like brown dwarfs, like they're a bit bigger than Jupiter. But just again, because of our detection sensitivity, it's hard to find very small things like this. But those are the two ways we found rogue planets: directly imaging them floating through space, or with microlensing.
Great, thank you. And the next one isn't as such a question, but a comment from Mike Frost, who's the director of the BAA historical section. He says, "Thanks, Jessie, that was great fun. My predecessor, Mary Evershed, the first director of the BAA's historical section, wrote Dante and the Early Astronomers about the astronomical themes in Dante's Divine Comedy, which you mentioned in your talk. His astronomy was quite well informed for the time."
Yeah, it's definitely the earliest I can find, you know, in my probably very Western centric ability to search through. It's some of the earliest like proper setting stories off the surface of the earth that I could find.
And then from David Boyd, we have, does the rate of planetary system formation change over the lifetime of a galaxy?
Ooh, yeah. Okay. So there's a few ways why this might be true, and it's something that we're thinking about at the moment. For a very, very young galaxy, early in the lifetime of the universe, there's not a lot of metals yet. So astronomers call everything that's not hydrogen and helium metals. So these first few generations of stars that formed early in the universe, and you know, the Milky Way is getting on as old as the universe, were mostly hydrogen and helium. So the protoplanetary disks that formed around those didn't have a lot of things like carbon and oxygen and nitrogen to build rocky worlds, for instance. So these first systems would have just been able to make gas things. But then as generation after generation of stars, you know, form carbon and hydrogen, they go supernova, they seed the galaxy with this heavy material. You know, I'm sure you've heard this adage, like, you are made of stardust. Like we're all supernova remnants right here sitting and listening to this talk today, because all of the heavy elements that make us up come from these generations of stars. So over the lifetime of a galaxy, if this galaxy started early in the universe and was predominantly metal poor, so not a lot of metals, then it would have formed very different types of planetary systems than what it's doing right now. Like right now, the Milky Way is just happy churning out rocky planets all over the place because there's enough of this solid material around. But very early in the lifetime of the galaxy, that wasn't the case. There aren't as many rocky planets. There won't be as many rocky planets at the very start of the Milky Way galaxy as there are now.
Thank you. And then we have a question from Billy Russell. He says, I've been marking TESS light curves for 2 years. Recent results show I have 3 TIC transits with my name on them. how do I track these TICs in the archive if one is in fact shown to be a verified planet?
Sure. So what our group is doing is uploading. So any citizen science finds that are found with Planet Hunters get uploaded to a website called ExoFOP, the Exoplanet Follow-up Observation Program. I'll put the link in the chat. Can I post in the chat? Yes, here, I'll put it right here. exofop.ipac.caltech.edu, and they get uploaded as CTOIs, which is community TESS objects of interest. Then the TESS project looks at the CTOIs and does their own check with the data, and decides whether or not to promote them to TOIs, which is TESS project objects of interest. And then those TOIs get followed up with bigger telescopes on the ground to get spectra, to get masses, to get atmospheres, and then those get written up as papers. In terms of how you would track it, I guess you would check ExoFOP and see if it got uploaded as a CTOI, and if it didn't on the Planet Hunters Talk forum, you'd be like, hey, is this going to get uploaded? And then you could see if it ever gets promoted to a TOI. I think that Nora Eisner has been the one in charge of Planet Hunters. I think she's been doing a pretty good bookkeeping job of making sure that the citizen scientists who are involved in individual finds get credited and get on papers, but she's the one who is doing the bookkeeping of that. So if you're at all concerned, then you can send her an email. I think she's on the Planet Hunters Talk forums, or you can send her an email.
Cool, thank you. And now we have a question from Darryl Dobbs. Are you looking for biomarkers with molecules containing phosphorus other than phosphine?
Oh, yes. Okay. So this is related to this recent discovery of potential discovery of phosphine on Venus and what that might mean for life on Venus. So really interestingly, when we talk about biomarkers, a lot of what we're thinking about is like water and methane and oxygen. But there's a lot of geological and processes that can form these. The really rate limiting step for life on Earth is phosphorus. If you look at the equation that life uses to turn fuel into energy, it's rate limited by phosphorus. It's like 100 carbon atoms and 80 oxygen atoms and a bunch of hydrogen atoms and one phosphorus atom to make this whole equation work. So phosphorus is like super important for life on Earth and hasn't really been thought about as much. It's hard to measure phosphorus in, for instance, stellar spectra. So what I would say is that we're looking for any molecule we can find. That's kind of the level we're at with exoplanet atmospheres at the moment. We're just trying to find anything. So if there's anything that has phosphorus in it, we're also looking for it. Mostly what we're finding are things like oxygen and carbon dioxide and methane, where you're like, okay, that's not great yet. In terms of a biomarker, there were problems with phosphine. I think there are still problems with phosphine in terms of how it can get created in ways that aren't biological. Basically, the big result when they came out, they were like, there's either missing physics or missing chemistry or missing biology, and we don't know which one it is. And everyone was like, life on Venus! Which I think for the authors was like, or missing chemistry or missing physics. So we don't have any like smoking gun biosignatures yet that have phosphorus in them. But I would say we're looking for anything and everything we can find and get funding to look for. The important part is, the last part is important.
Great. And just on the previous question with the, to do with the Caltech website,
Mm-hmm.
and it's the link only went to the panelists, but I'm not sure it worked. But I think I might have found it.
Oh, great!
Would you
Sorry,
mind
I was just trying to remember from the top of my head.
Yeah, no, I fully understand. If I share my screen for a moment, would you then be able to confirm, and then people can see if that's the right one? So if I go to that, does that look like what you were?
Yes. So there's that's the CTOIs. There's 1,430 that have been uploaded. So that third column there where it says promoted to TOI, those are the ones that the project looked at and was like, oh yeah, that's a legitimate planet candidate that we missed. Let's put it in.
Great. And what I'll do, I'll leave that up for a minute or two. So if anyone wants to note down the address, they
Yeah.
can see it. And we've had one more question come in.
Sure.
And this is from David Patterson, who says, thinking about the limits of magnitudes and noise levels, what's the current maximum distance we'd be able to reliably detect Earth-like planets around sun-like stars?
Oh, yeah. Okay, that's interesting. It kind of depends on the technique. With current technology, so Kepler went out to a few thousand light years. So really, like if you think about the scale of the galaxy and the fact that we're 30,000 light years from the middle, we've actually really only searched this like little bubble around us in our galaxy. And we're doing a lot of extrapolating from there when we talk about rates in the galaxy. We've only really searched our local bubble, and TESS is looking even closer because it's only got 10 centimeter telescopes. Microlensing, which is the one that I mentioned, has found the furthest planet, which is 26,000 light years away towards the center of the galaxy. It's sensitive to very large distances, and in fact, there was one tentative microlensing detection in the Large Magellanic Cloud, because the way that microlensing works, the magnitude change in the star that you're looking at can be huge, can be many magnitudes, like it can get many times brighter, as compared to things like transits, which relies on the planet blocking a little bit of the light. As you probably heard about this earlier in the day with Cheops, that's blocking like parts per thousand of the light or parts per million, whereas microlensing is relying on many times larger flux coming through, so much more detectable at much larger distances. So at the moment, I would say that's a tentative detection in the Large Magellanic Cloud. So the Large Magellanic Cloud is probably the furthest away we're talking about being able to detect planets like the Earth around stars like the Sun.
Great, thank you. What I'll do, I'm just going to stop sharing my screen now so I can see, get back to see, because it's blocking my view of YouTube. I'll just check there's nothing, excuse me, trying to do too much multitasking at a end of the evening for me. I'm just struggling to, if I do, I'll just temporarily do that instead. And yeah, there we go. So I think that's back to how it was. I'll just have a quick look on YouTube. No questions have come in there. So with no more questions coming in, I'd like to say thank you very much, Jessie, for coming and giving this talk to us. And I think it's one of the advantages, one of the few advantages of having Winchester as an online event this year, is that it makes it easier for us to have someone from a great distance to come and give us a talk, which was both very entertaining and fascinating. Thank you very much.
Yeah, well, thank you for having me again. It was a pleasure. I was glad I was able to talk to the group, and very honored again to be asked to give this memorial lecture.
Thank you very much indeed, Jessie. Thank you, Andy. So no more questions. Alan Dale, do you want to add anything before we go?
Yes, just to say thank you very much indeed. And also thank you for all the speakers we've had in the course of the afternoon and evening. And also remind people, thank you very much to Anne Davies for organising the speakers and making sure we had a good evening. And it's good to see that we got sort of similar numbers on YouTube and on the webinar. That is we would normally have at Winchester Weekend. And just remind people that, of course, we have Winchester Weekend booked for next year at Sparshot College. And as somebody's just reminded me, don't forget your keys. It's a very in joke. So if you come to Winchester Weekend, you'll understand what that means. Thank you very much indeed, Jessie. Thank you very much indeed. Thank you.
Andy, do you want to just remind people for the webinars that are coming up over the next few weeks, and we've got the spring meeting as well?
Yes, so we've got the next webinar, which we have, is the Great Debate, which is going to be by Dr. Nick Hewitt, and that's going to be on Wednesday the 14th at 7 p.m. in the evening. People may have noticed that the radio astronomy section have been doing their own set of Zooms, and those are continuing every few weeks, and you can find them on the BA website. And then we've got the one-day spring webinar, which is on Saturday the 24th of April, and it's on cosmology, galaxies and exoplanets, with a one talk at 11 and another at 2 o'clock.
Thanks very much indeed, Andy. So without further ado, we'll sign off now, and thanks so much indeed for joining us either on YouTube or on the BAA Zoom link as well. Goodbye.